Zipcast.
So that means usually you train a neural network at once.
Exactly. You give it everything and you say, find the pattern in all of this. It's doable when you have lots and lots of data because you will find a pattern. When you're staring at several different images, eventually you start to see what is the commonality amongst all of it. But when you have a small amount of data, you can't do that.
Podcast zum thematischen Einstein-Semester 2023-24. Small Data Analysis. Folge 2. Künstliche Intelligenz und kleine Datensätze.
So, hallo. Herzlich willkommen zur zweiten Episode unserer Podcast-Serie über kleine Datensätze. Mein Name ist Markus Weber. Ich bin Arbeitsgruppenleiter am Zuse-Institut in Berlin und wir haben uns ja schon in der letzten Podcast-Folge kennengelernt. Heute sprechen wir über kleine Datensätze und künstliche Intelligenz. Und der Experte für künstliche Intelligenzmethoden ist Vikram Sunkara.
Hello Markus, thank you for having me.
Und Vikram Sunkara kommt aus Australien und hat viel im Bereich erklärbarer künstlicher Intelligenz gearbeitet. So, explainable AI is your research topic.
That's right. I'm the head of explainable AI for biology here at the ZIP. So in terms of small data, we work on rare diseases. And so a lot of our focus is really on understanding what artificial intelligence, what deep neural networks are actually doing, because there's really a huge scope in their application in medicine.
Yeah.
So in terms of small data, we are interested in studying or finding phenomenon related with rare diseases. So we have connections with the Charité, where they have clinics which are specializing in rare immunological and surgical diseases.
So what is rare diseases? What do you mean by rare diseases?
They might be genetic diseases, for example, like a certain mutation which has happened, or rare disease in the sense that the patients are exhibiting inconsistent symptoms, where they cannot classify them or group them into known disease pathways.
And what kind of data do you get from the Charité?
So different projects have different kinds of data, but we mostly focus on scores. So the clinics which are taking care of the patients will have some clinical scores, which they measure like for these particular patients over a period of time. So we have one patient with many observations, but the difficult part is that we don't have many patients. So therefore, it's hard to identify what exactly is driving the disease.
Mm-hmm. So you don't know which parameter is important from all the parameters you measure with one patient, right? This is a problem. So the high dimensionality of the data set.
Exactly.
But only for a few points, so to say.
Exactly. We have many different readouts because in the clinics, there is a well-established set of clinical factors. But the clinical factors are to help delineate the already known diseases or the more commonly occurring diseases. And when we only look at it through those clinical factors, they might not delineate the rare diseases. They usually do not. That's why it's so difficult to treat them, because they don't easily separate with respect to known clinical factors.
Okay, so maybe that's something you have to explain to us in your example. What is meant by there is a gap in the statistics?
I would not strictly call it a gap in statistics, but rather a different approach. Statistics, for us to be able to give confidence in something, it's about a difference in distribution. But in this case, we have so little samples, the aim maybe one day would be to have a separation in distributions if we have enough patients. But for the first step, what we're really more interested in is that are there any factors where we can separate these particular patients? Mm-hmm. Our roles as mathematicians with the clinicians is really to give them clues on where to look, like which factors might be important or which factors are separating. So we don't begin with the statistical process we take like a more machine learning or an artificial intelligence approach to it, and then give some hints on what could be, let's say later down the track when we get enough samples, become statistically significant.
So you apply artificial intelligence methods to discriminate between a healthy and a diseased patient. And often it is said that artificial intelligence methods need big data sets. But now you say that there is only small data because it's rare disease. How does this fit together? How does artificial intelligence and small data fit together?
I would like to answer this question by giving an analogy. So artificial intelligence is a tool, like many other machine learning methods out there. Artificial intelligence is only one type of tool where we use these concepts of artificial neurons. And like most tools, we usually see it as a single function thing that it has been made for. But we also have tools which can do multiple things. And so I see artificial intelligence as a multi-tool. Maybe an analogy across to like a drill, which has the hammer function, has the drill function, and also the screw function.
Okay, I see.
Right? Like that's what I kind of want to say. And of course, you might say, okay, why do I need a drill with a hammer function to screw in a little bolt? But the thing is, it has all the capacities. It has the capacity to be able to do all three things, but we just have to change how we use it. We have to rethink how we utilize the tool for the task that we have. At the bottom line, neural networks are there to bisect information. Its task is to cut up the data into meaningful pieces to find a representation of the data which answers the question that you're asking. And this is independent of the size of the data. The size of the data makes it complicated on how you learn. But the tool itself, its objective is to look at the data, cut it up into meaningful pieces, which it can then use to answer the question that we have.
I can imagine that in the clinics, AI is not tailored for solving the question, what is the disease? But maybe it's more tailored for consolidation of the doctors. So if the AI tells the clinician, oh, I also see the same pattern, or I also decide the same way you do in this and that situation, it's a feedback to the experts, or they feel more confident of deciding in this and that way.
I like the way you put it, the idea of consolidation. If you look at, let's say, progression of knowledge over, let's say, centuries now, we used to spread knowledge by word of mouth. One would say something to the other, and then knowledge would be stored in an individual's brain until it is then again passed on to someone else. And then we did this for a really long time. Then came the printing press, right? So no longer knowledge had to be given live from person to person, but you could give the knowledge and we can send it around the world, and then the person can have access to that knowledge at any point in time. Then came the internet, which is again another leap forward, is that now you don't even need that book, right? Like any individual can have access to knowledge. So it's this conglomeration of all libraries, right? And now comes the next level, and this is what I kind of see the AI done, is that now it has taken all of those and now compressed it into like a new structure. And it's kind of compressed within that architecture. And this is how I see it, is that all the patients which came before and all the patients in all the other clinics can all be consolidated into one structure which a clinician can use, right? You can interact and you can harness this information, and it's kind of compressed. And the fact that we can condense such complex information down into a certain structure, that's the breakthrough, right? And now every single doctor, wherever they are, can have access to this. They can train into and encompass it inside a little neural network, and then they can share that neural network. I think this is where we're going to go to in the future, is that imagine that every single clinic has a certain set of patients. And then, of course, they train the patterns that they see in their clinic. But maybe then once in a while they can then share. They can bring that same pattern around and say, okay, what's put it all together, and now we have like a new architecture, or like a new machine which has consolidated all of that knowledge.
Mm-hmm. So artificial intelligence is one way to store knowledge.
It's an active way of storing knowledge, because this is a little bit different. It's a bit more like our brain in the sense, like we have an active way of storing. It's not like a book. We don't have it like, here is the sentence, blah, blah, blah. Mm-hmm. The pattern of it is stored within our brain, and then we access it.
Mm-hmm. So you have like a geometric interpretation of what artificial intelligence does with the input data to get the output result. Maybe you explain to us this geometry of partitioning data or cutting data into pieces and folding it. Maybe you give us a clue what is happening geometrically.
I think this is a very hard thing to give a visual explanation over audio, but I will try. So what neural networks are essentially doing, you give it some input, and some neurons decide to turn on or turn off. And if you think about each neuron as a gate, do I switch it on or off? So you can imagine then each neuron, if I said, okay, if I took my data and I colored in all the regions, all the data points which were switched on and all the regions which were switched off, what would that look like? That would look like a cut in your data, right? Your data is partitioned. So a neuron partitions your data into, let's say, on and off. Now imagine you have a second neuron which does this as well. So now this second neuron is going to cut your data in another way. Mm-hmm. So like that, what you're doing is you're cutting your original data into small, small pieces.
And they have like labels on, off,
exactly.
patterns.
Exactly. And so now what has happened is that we've turned your data into, let's say, another signal, which is just, is it on and off for these? So each piece has a new representation. And now the breakthrough in artificial intelligence is that we just don't stop there. We do this again. Mm-hmm. Mm-hmm. So the pieces that you've cut, we cut again. We cut again into more pieces. This is what we call deep learning. Yeah. And this way has been proven that we can hone down into exactly the region which is specific for making the decision that we want.
So by cutting it down and down, you reach that region in data space where the important deciders are.
Exactly, where it's easy.
Where it's easy to decide.
Where it's easy to decide between what we're interested in and what not.
So, but then you say, after cutting comes folding. Usually the output of a neural network is not like all the pieces, but low dimensional.
Exactly. So then comes the next part, is that you might have several pieces. So then it starts to fold them together. Mm-hmm. So what is similar will be moved closer and closer together. And the pieces which are further away are going to be moved further apart. And then once again, it becomes easier to make that decision. Mm-hmm. So it's very easy to create what we usually call like decision boundaries. So this is what we're interested in rare diseases, is that we have all these different factors that we're looking in. We try to give this to the machine and ask it, okay, what's a good piece where I can distinguish it from the rest?
Maybe there is a difference between how usually diagnosis is done and the way you described it now. Is it like this?
Yes. So I see it as a two-step process. The power of the artificial intelligence is that it's not biased on how it does the cutting. So we only want to make sure that how it finds it is robust. So therefore it can go and it can make very complex cuts. So very complex ways in which it can find why a particular patient is different from the other patients. Then this gives us a clue. And this is what we're here to do as mathematicians, is to give the clinicians clues where to go and look. And then this is where explainability and things come into the picture, where we then go back and we say, okay, why did the machine cut this? And then based on that, they can then go and do further experiments and be more clear or get more statistics and such and be like, yes, there is a decision barrier here, where we have hinted where the decision barrier could be.
So if you think about what you have done so far, what had an impact on the people in the clinics?
So for me, at this stage, of the development of AI. For me, a win is when a doctor in the clinic can start to see value in the decisions which the architecture is making. Because that's what we want at the end of the day. Like, it's still obviously going to take a long time to actually have it applied directly to the patient, but we want clinicians to feel confident and secure and safe and understand what is happening within it. And if they start to see patterns which they have already built in their own minds from their experience, and they see the machines making the exact same patterns, we start to get some confidence and they start to see the value in such things. So this, for me, is a win.
We said that there is no method that we take from the shelf that is already prepared and solving our problems. And we talked about the impact of our methods to the physicians. But maybe there's the other way, that diving deep into their fields of expertise, so diving deep into clinical problems, drives mathematics. Is it like this?
Very much so. Very, very much so. It drives it, I would say, much further than if we're working on regular diseases. Mm-hmm. Because what, in my experience, is when I'm working with, let's say, rare diseases or problems where the answers are not straightforward, is that then we have to start studying structure. And this is where the mathematics starts to come in, the structure of the data, right? So we're usually talking about some sort of topological structures or geometric structures that we have to be very careful, and we have to be very precise which mathematics we use to represent these structures. And then we also have the structure of the neural networks. So these themselves are also mathematical objects. And then it gives us the questions like, can we give guarantees? Can we merge two architectures together? What is the intersection between these things? These are all mathematical questions. Mm-hmm. For example, you want to merge two neural networks together. If I say, okay, a neural network is actually a certain type of topological structure, can I always merge two topological structures together and then get a new topological structure? Will it be the same as just the union of the two, or do I create so it gets really interesting, and we wouldn't ask these questions if we had plenty of data. Mm-hmm. This is where we really have to go really deep to be able to give the guarantees, because the patterns don't reveal themselves easily to us. And this is where we start writing the theory, and of course then the theory can be applied to the other cases as well. But here the mathematics to come in and say the small thing that we see is reliable. The small data forces us to study these things. There's no way we can get around it. Mm-hmm. And this motivates us. And there's no way that we can overcome this hurdle without studying these mathematical structures, without giving these results, without giving these guarantees.
Mm-hmm. And in having this difference in how to use the method artificial intelligence or how to use machine learning, that also calls for new mathematics, I guess.
Absolutely.
Or calls for mathematical research, I guess.
We need a lot more mathematical foundation around how learning is actually happening within these architectures. And we need a lot of mathematics to describe what has been learned as well. Mm-hmm. And so when we know what has been learned, and if the way it is learning is robust, then we can give some confidence and some guarantees to what we have learned. Mm-hmm. And so it's about adaptation and understanding. It's not about like rote learning, like knowing. Knowledge is not intelligence. When we test for intelligence, we say something is intelligent when we give it a system, or it belongs to a system, and then it breaks the system, right? To break a system, it has to understand the system. This is how we deem intelligence. Like when we do experiments with birds or animals, we usually set up some system, and then the intelligence comes in when that system is broken. And this is how we know knowledge is not equivalent to intelligence. And so what we focus on in classical schooling is knowledge, to put more and more knowledge into people. But having knowledge is not intelligence, right? Intelligence is the ability to use knowledge. That's what we want in students, not that, okay, well, we go and teach, the student knows as much as we do now. Who cares? I already know that. Mm-hmm. But what we want the student to know is to go beyond, right? To go a step further where I could not have gone, or I did not see to go. And that's what we want this AI stuff to do as well, right? In some way.
Coming back to your analogy, the classroom. So you said that you have a classroom of artificial intelligences, let's say. And I would expect, of course, that the most complex artificial intelligence, having the highest number of neurons in it, being able to learn everything, that's the intelligence that wins in the end. But I guess there is something like overfitting or something like that behind it.
You're right, in the sense that a big architecture has the ability to, let's say, fit more information inside it. But given the analogy that we discussed before in terms of pieces, so it's so big that it has all these different pieces, but it might not have a relationship between the different pieces. Right? So it does not necessarily understand good structure or relationships between the different pieces that it has. The nice things about neural networks is that we can actually decrease this complexity. So there are methods out there, or this is how it is done, is that first we do train a very big one, which can see everything. In the second step, we would want to reduce it. Mm-hmm. We want to simplify all the different pieces into some meaningful groups.
Yeah. What do you think? What is the missing research in the field of small data analysis and artificial intelligence?
So the research questions are going to go into how do we learn from small data? How do we come up with a learning strategy for the small amount of examples that we have observed? We still make hypotheses from very small observations, right? But just doing that, of course, is not robust. We have to think about, okay, what tests can we put?
Mm-hmm. So here we have a situation where the artificial intelligence is a tool to make us learn. So it's not the artificial intelligence that learns from the data, but is our tool to learn. So it's a tool to train the experts. Not the artificial intelligence alone is trained, but this as a tool trains the experts.
Yeah, really
and
well
this
put.
is what often is in small data analysis, that this interaction between knowledge and method, that's very important when you have small data sets.
So I think what we really need is encouragement of students and researchers who want to bring mathematics into AI. Because this is not going to be such a simple task. There's a lot of young people now that are coming up. They're also seeing this. It's definitely not going to be like one field which is going to be able to do it. We're going to have to bring together different mathematics from different fields, different schools of thought together to be able to answer these questions.
Mm. Yeah, that reminds me of the last workshop of the Thematik Einstein semester, where a psychologist, she said that our problems these days are interdisciplinary. So you cannot solve a problem without thinking interdisciplinarily. And that means that we should encourage people to work together with other fields, also using other fields' research culture for their own methods. Yeah.
That's right, Marcus. So our focus today is not so much artificial intelligence themselves, but rather how they motivate us. Like the problems that arise in analyzing is actually a mathematical challenge. The tools and methods that we have to specially develop for this task is very different from the classical methods that we have. We have to bring a lot of theory, and we have to develop new methods to be able to give guarantees.
Mhm. Okay, dann also Dankeschön, Vikram.
Thank you very much for having me. It was really a lot of fun.
Ja, mir hat es auch sehr viel Spaß gemacht. Es gibt noch so viel zu entdecken im Bereich kleine Datensätze und mathematische Methoden. Und das werden wir auch in der nächsten Podcast-Episode wieder aufgreifen. Bis dahin alles Gute.
Zipcast. Eine Produktion vom Zuse-Institut Berlin. Gefördert vom Math Plus Berlin Mathematics Research Center und der Einstein Stiftung Berlin.